computational reproducibility. So before starting the talk, I wanted to tell you a little bit about myself, but I think that Chiara has done an excellent job at that. So yeah, I'm a PhD student in neuroscience at the Max Planck Institute in Frankfurt, Germany. I'm also a core contributor and maintainer of the Turing Way. Specifically, I provide infrastructure support to the project, and I will tell you a little bit more about what infrastructure means later on. So I've divided this presentation in two parts. The first part is to show you what the Turing Way is, in case you're not familiar with it. And the second part is to tell you a little bit about its advices on computational reproducibility. So, okay, what is the Turing Way? If you're familiar with the Turing Way, you probably are familiar with this book on reproducible science. But the Turing Way is not only a book, it's also an open source project, a culture of collaboration, and a community. And I will explain what each of these things means throughout the talk. And before starting, I also want to give a big shout out to Scriberia. It's a drawing agency, and they have made all these amazing drawings. And you can actually reuse them as you like because they're under a CC BY license. And you can do so by entering the Sonoro page of the Turing Way. You have all the illustrations there. Maybe you recognize the person in the book drawing. She's Kirsty Whittaker, and she's the project leader of the Turing Way, actually. And now she's also the program lead for tools, practices, and systems at the Alan Turing Institute. So Kirsty and others a few years ago had this awesome idea of creating an online book whose moonshot goal was to make reproducible research too easy not to do. And this is a screenshot of how the Turing Way looked back then. Now it looks a little bit different. It has multiple guides. One of it is for reproducible research, and it has a lot of chapters, as you can see. You're welcome to explore it further following these links. In the chat, there is a link to my slides today. So all the links that I'm mentioning and showing, you can follow them if you enter that Sonoro page. But the Turing Way has also expanded and is not only now a guide for reproducible research, it's also a guide for project design, a guide for communication, so how to communicate your research to others in a more efficient manner. It's also a guide for collaboration and a guide for ensuring that your project is also ethical. But as I said before, the Turing Way is not only a book, it's also an open source project. And what this means is that everybody can freely read, reuse, distribute, modify, and help develop. And the project belongs to the Turing Way community. Everything is under a CC BY license. And for example, the presentations are hosted on the Sonoro page of the Turing Way. And here you have the link as well. But it's also an open source project because all the content of the book is hosted on GitHub. And you can actually contribute to it, submit a pull request, or open an issue there. And it's also an open source project because it's built with other open source tools. So as I said before, what I do for the Turing Way mainly is to provide infrastructure support. And this means the Turing Way uses JupyterBook as its platform for hosting the book online. And this is an amazing tool that is built by the Jupyter people. So the same people that build the Jupyter notebooks. And if you're interested in the Jupyter book itself, we gave a tutorial for the Jupyter conference, which was like a month ago, with Malvika Sharan, who is the community manager of the Turing Way, and Sarah Gibson, who is a research software engineer at the Alan Turing Institute. And you can access all that material following that link. The Turing Way is also a culture of collaboration. And what this means is that it's especially welcoming it welcomes everybody regardless of your background, of your discipline, of your knowledge, but it's a great place to get involved in your first open source contribution. So if you're not familiar with GitHub, if you never contributed to an open source project before, this is like the best way to get familiar with it. There's a lot of nice people who want to show you how this open source collaboration is done. They have a lot of patience. So if you want to get initiated on this is a great place to start. And importantly, you don't have to necessarily contribute content to the book. There are many things that you can help develop in the Turing Way project. So you can also read, share resources. You can fix bugs, typos, errors. You can engage informally, meaning you can just get in touch with us to discuss open science or reproducible research topics. We always love discussing that. You can review other people's pull requests. You can help translate the book. There's a lot of effort going on right now for doing that, especially in Spanish. And then you can also help improve our culture, meaning maybe you have an idea of how to create an attractive event for people or stuff like that. And very importantly, everybody gets acknowledged for their work. It doesn't matter what you did in the project. So the way that we acknowledge people is by using this all contributors bot. And so the way it's done, I don't know if you can see my cursor, but in the GitHub page, there is a contributors table and you get added to it using a pull request to the all contributors pod, and you get an emoji for the things that you did. So for example, this person fixed the bug and this other person contributed some content. And finally, the Turing Way is also a community, and what this means is that anybody can join and contribute, and the direction and the goals of the project are determined collaboratively. And we have a lot of we have a lot of community events, sorry. We have what is called collaboration cafes and co-working calls, which are meetings online. We use Pomodoro timers to work on the project or to discuss relevant topics. Collaboration cafes are done every 2 weeks, and they are like 2 hours long, and co-working calls, they are done weekly, and they are 1 hour long. And then we have book dash events. They used to be in person. This was back in February in London, but nowadays we are hosting them online. And actually this week we have one book dash event. And as I was saying before, that's the reason I couldn't participate more thoroughly on the Break Hackathon Ostia. But you are welcome to apply for our next book dash event. They are super fun. And all of these are organized by the amazing community manager of the Turing Way, Malvika Sharan, but you're also welcome to host these events yourself if you're interested. And currently the book has more than 200 contributors, but we are always looking for more. So if you are interested, I'm going to link all the ways that you can get in touch with the Turing Way at the end of the talk. Okay, so now for the second part, I talk about what the Turing Way is, and I'm going to show you some advices about regarding computational reproducibility that Turing Way gives on its book. So before talking about computational reproducibility, we have to make sure that we are on the same page about what reproducible research means. And this table is included in the Turing Way book. And what it says is that we're talking about reproducible research when we perform the same analysis than another person on the same data set and we achieve the same result, which is different from replicable research where you have different data sets but similar and you perform the same analysis and hopefully you get a similar result, or robust research where your data set is the same, but the analyses are different but similar, and you hopefully get a similar result as well, and generalizable research where your data set is different and your analysis is different but similar. I think that we can all agree that all these four are important for the advancement of science, but if we cannot ensure that our work is reproducible, then we can hardly ensure that it's replicable, robust, and generalizable. So reproducible research is like the lowest standard we should aim to cover. And the Turing Way has a lot of chapters on reproducibility, not only computational reproducibility. So it has chapters about how to ensure that your data collection is reproducible, how to then open the data and make sure that everybody else can reuse it, how to also think about your research ideas in a reproducible manner. But sadly, I cannot talk about all of these, so I decided to focus on the computational reproducibility part. But if you're interested in all these other steps, you can head over to the online book. And yeah, what do we mean by computational reproducibility? I think that is important for achieving computational reproducibility, to cover these 4 steps. They are not in order, of course, but it's important to cover the 4 of them. So it means to track changes to your code, so use a version control system. It means to write clean, understandable, and error-free code. It means to save and share your computational environment, and it means to make your code open source. Just a few things before starting with this part of the talk. From each of these steps, one could give days, if not months, of tutorials. So what I'm going to say is a very brief overview of these steps, and by no means is something that is comprehensible. You should read further to really understand what each of them means. And then another important point to mention is that this is not only valid for the cases where you're, for example, trying to create an open source toolbox. These 4 steps are also valid in the case where you're just wanting to make your code for your particular experiment available for everyone. So if you're just creating code to accompany a paper, these 4 steps are also valid. And for these particular examples, I'm going to use the Python language, programming language. But the Turing Way does not have an opinion about which language you should use. So you could read about other programming language alternatives there. So yeah, for the first part is to ensure computational reproducibility, you have to track changes to your code, meaning you have to use a version control system. And what I mean by version control system is a system that records the changes to a file or set of files over time and provides access to any specific version. And you're actually familiar to many version control systems because Google Docs or HackMDs are version control systems. But of course, for code, the most well-known is Git, and the changes are recorded using snapshots in Git, which means that every time you take a snapshot, you record how your whole project looks at that point in time, not only the files you've changed. And it's a distributed version control system, meaning that anybody who has access to that Git repository has access to the complete history of that project and the complete versions. And Git differs from GitHub. And I think this was very nicely explained by Stefano on Tuesday, so I'm not going to dig further into that. Just to mention that GitHub is a web and desktop API interface of Git repositories, and is where most open source software is hosted. But there's a lot of resources about version control, and it's a very wide topic that I cannot cover here, but I also saw Stefano's talk on Tuesday, and I think it was amazing. So I really cannot add further into that, and I will leave this topic here, but I will also recommend you to read the official documentation of Git and the ProGit book, which is amazing. And as a personal recommendation, I think that what really made me understand how to use Git commands was actually to understand the logic behind Git, not only just to memorize those commands. So if you really understand how, the logic behind Git branching, or if you understand what a working tree is, a staging area is, what a .git folder has, all these things make it easier for you to really understand what the commands are doing. So to ensure computational reproducibility, it also means to write clean, understandable, and error-free code. And there are a lot of tips to achieve this. The first one is to use a code style guide. And a code style guide is a set of conventions on how to format your code. So for example, it's going to tell you how to indent, how to comment, how to import packages, how to name your variables, and so on and so forth. The standard code style guide for Python is called PEP8, and this is, how, for example, how PEP8 likes to import packages. Packages should be imported in separate lines. You shouldn't import 2 packages on the same line, for example. Another example is how to space your code. And as you can see, if you are multiplying 2 things, then you shouldn't add a space, but if you're adding or subtracting, you should. So yeah, there are many conventions such as these ones. I'm linking to you the PEP8 style guide below, and you can follow that link to see all of them. But there's another really cool tool that has to do with this, which are style guide enforcement tools. So what a style guide enforcement tool does is it reads your script and it detects when you're not being compliant with that convention. And it throws an error when it detects this. So the most well-known, at least in my opinion, for Python is flake 8. Flake 8 detects every time that you are not being compliant with the PEP8 convention. So I created an example here where I'm running flake 8 on something that I'm calling bad file. And as you can see, PEP8 says, Look, in line number 1, you have an 501 error, which means that the line is too long. You have 80 characters when you shouldn't have more than 79 characters. And it also tells me, look, in line 3, you have an 2025 error, which means missing white space around operator. And this is something that is very much used in open source toolboxes such as scikit-learn or pandas. They usually use Flake8 for the code. And besides this tool, you also have another one, which is called automatic formatting tools. And what they do this time is that they read your script, but they don't throw an error when they find that you're not being compliant with the convention. What they do is actually change your code to be compliant with the convention. And one of the most well-known for Python is Black. And it tries to follow paper 8 convention, but it's also opinionated on other regards. So for example, Black doesn't like if you assign a variable so many vertical white spaces when you could do so in a flattened version. So it's going to, if you equate J to this list, it's going to change it to look like the second. And the second tip that I would give for writing clean, understandable, and error-free code is to actually perform code review. And this means that you ask another programmer to look into your code and evaluate it. And by evaluating it means not only that they detect that maybe you are making an error, it also means that maybe they have tips on how to optimize your code in some way, how to use another method to optimize it. And during this process, you learn a lot. It doesn't matter if the code reviewer has the same programming experience or is in the same programming experience stage as you. We all have different tips and tricks that we know, so we always learn a lot when we perform code reviews. And there are two ways where you can do code reviews. One is in a synchronous manner, meaning that you're co-located with your code reviewer. You're in the same room, looking at the same code at the same time. For example, a way of doing code review is to present your code during lab meetings. As you were to present a paper on a journal club, you present your code. Maybe you're stuck on some part of your code, or maybe you just want advices on how to make it more, how to optimize it. And lab meetings are a great place to show that. And there's a great blog post about how to do code reviews in lab meetings by Fernando Perez, and you should really read it. It's in his personal website, I think. And another way of doing code review actually is in a synchronous manner using GitHub, for example, pull request in GitHub. And you have seen an awesome presentation of how to do this on Tuesday during the ICA Aroma package demonstration, when they were showing how each other commented on each other's pull requests. This is a code review done using GitHub platform. And the third advice on how to write clean code and error-free code is actually to test your code, of course. And I love this phrase in the Turing Way book, which says, you should not skip writing tests because you're short on time. You should write tests because you're short on time. If you test your code, you make sure that if you have made an error at some point, you're not propagating your error throughout your code, and then you have to go back and change everything because you realize that you have a bug. And the good news is if you don't test your code so far using automatic tests, you're probably already testing your code in some way. So whenever you load some data, here I'm just assigning data to a random array, but in a real case scenario, you would read a CSV file, for example. You probably print your data to make sure that it looks the way that you were expecting. Well, this is a way of testing that your code is doing what you expect it to do. But there's a more automatic way of doing this that is using, at least in Python, the assert command, where, for example, suppose that I know in my data the number of rows equals to the number of observations that I have, and I know that I've observed 3 variables, or I have 3 instances in my data. So you're going to use the assert command to make sure that your data in its first dimension, which is going to be rows, has the expected number of rows, which in this example was 3. And as you can see here, the number of rows equals to 4, so it's going to throw me an error. And importantly, in the assert command, after the comma, you can tell the assert what should print as an error. So here it says shape mismatch. You can be more explicit than this and make the assert command throw an error where it says what the real rows were, so the actual number of rows that you have in your data, and what you expect it to be. But as you can see, this looks a little bit cluttered. So fortunately, we have sorry, I'm going to show you afterwards. But just a side note on this, assert commands are great. You can put them throughout your code, but there's a better way of doing this even, that is doing what's called unit test. So in a unit test, suppose that you have a function in your code that, for example, you want to take the 5th power of some variable. And you have that function, takes x as an input. Then if you do unit test, what you would do is to create a test based on that function, which is usually called test underscore and the same name as the function that you're testing, and use the assert command in a way that you know its inputs, you know its outputs, you make sure that the function is doing what you are expecting it to do. And unit tests are great because they force you to also write modular code, meaning that creating a lot of functions and classes that do just one thing. And this is a great way to making sure that your code is clean as well. But what I wanted to say before is that a great way to do unit tests and a great way to not write a lot of assert commands like the way I've shown you before is to use the testing framework. In the case of Python, the most well-known is PyTest. And what you can do with PyTest is that you can get a detailed information of your assert statements without having to give this string. For example, PyTest in this example says, oh, you were expecting a 5, but you give me a 4, for example. Another great advantage of PyTest is, or any testing framework, is that they allow for auto-discovery of tests, meaning that if you have your code in a folder and you create another folder inside it which is called tests, and you put all your tests there, you can run through the command line PyTest without any input, and it's going to run the tests that are inside the test folder. And there are a lot of other types of testing, not just unit tests. You also have smoke tests, which are done previous to unit tests. They are like initial checks to make sure that like some basic functionality is there. So for example, if you have a very basic class that all your code use, you instantiate that class to make sure that it exists. If it doesn't, then it doesn't make sense to keep testing in the code further. You also have integration tests that are usually carried out after unit tests, and this makes sure that everything works as a group. So if from one function you're taking as input the output of another function, integration tests are going to make sure that all those stuff is working fine. And you've seen examples of integration tests on the tutorial on Tuesday evening as well. And there are multiple other types of tests, and I don't have the time to cover to cover them all, but you can head to the Turing Way book and you have details of these other types of tests there. So for the third part, and is that for ensuring computational reproducibility, you also need to save and share your computational environment. And the Turing Way has this amazing table, which says, depending in what you want to reproduce and in the interaction style you want to achieve, then you choose one or other tool for saving your computational environment. So if you want to reproduce only the software and its versions, you have tools such as Binder and Conda. But if you want to reproduce the whole entire system, meaning also like your operation system, for example, then you need a tool like a virtual machine or a container. And I'm going to briefly explain each of these, but I'm not an expert on them, but you can read further in the Turing Way guide. So Conda is an environment management system, meaning that in Conda, what you can do is create environments that are isolated. So suppose that for my MEG project, I want to use the M&E tool, but I don't use M&E for any other kind of analysis. So I create an environment for my MEG project where M&E is installed, but every time I step out of that environment, I don't have M&E available anymore. And it's also package and version management system because you can use Conda to install packages. If you know Python, then probably you know pip. Well, in the same way that you can pip install something, you can Conda install something. But why Conda is something that makes your environment reproducible? Because inside the Conda environment, you have a file where all the packages are listed with their specific versions, and you can grab that file, give it to another person, and that person can Conda install that environment, and it's going to have the same environment as you. You also have virtual machines. They are not so frequently used nowadays, I think, and they are like, they package a whole computer as an app that can be run. So the problem with them is that they're very heavy, but they are very easy to use if you're not familiar with command line arguments or whatever, because you can extract them as an application. So for example, I could be using a Windows machine and I have a virtual machine of a Linux system. But fortunately, now we have containers such as Docker, which behave like virtual machines, but they're more lightweight because they only contain the individual components to operate the project. And I know that what I've just said doesn't really explain you the difference between a Docker container and a virtual machine, but it's kind of complicated and you should read it further into that. But this is what you should keep in mind. Containers such as Docker are more lightweight. And they allowed you to reproduce stuff like an operational system. And then you have tools such as Binder, which don't reproduce your whole system, only the software and its versions, but they reproduce it in an interactive manner. So you can use tools such as Jupyter Notebooks or Jupyter Lab using Binder. And the way it works is that you have a GitHub repository. In that GitHub repository, you have a file where you list all your packages and the versions of your packages. Then you go to mybinder.com and then you paste that GitHub repository here, you launch, and you're going to have access to that environment, and you can interact with that repository using the packages and the versions of those packages there. And the Turing Way has a lot of guides on Binder because one of the persons, Sarah Gibson, and one of the research software engineers there is part of the Binder project, so you should check them out. And finally, to achieve computational reproducibility, you should make your code open source. And what this means is make your code available for anybody to view, use, modify, and distribute the software for any purpose. And it's important to note that just by uploading your code to GitHub doesn't make it open source. You actually need a license to make it open source. And the word of license is complicated. Actually, the Turing Way has a very nice guide. But it's important to distinguish mainly two types of licenses. There are free licenses that make your software open source and proprietary licenses that don't make your code open source, of course. But inside the free licenses, you also have distinctions. So for example, you have a distinction between copyleft licenses and permissive licenses. The difference is that if somebody grabs your code and distributes it, which is totally something they can do because your code is open source. With a permissive license, you are not forcing the person who is distributing your code to use the same license as you. With a copyleft license, you do. And there's further distinctions between copyleft, but you can read them further in the Turing Way. And then another important point when you're making your code open source is that if you're interested in creating a community around it, then you should add some special files there. README files, I think that they are not optional. They should have it either if you don't want to create a community around it. And the README file, here is an example of a README file for the Turing Way. A README file should tell you the project name and main features, how to install it, how to run associated tests, the list of authors, contributors, how to contact you, and also any link to related material. So for example, if you're opening your code in companion with a paper, then you should link the paper there as well. But also, if you're interested in people contributing to your project, you should have a contributing MD file. And here you should say how to file a bug report, how to suggest a new feature, how to contribute changes. the roadmap or vision for the project, and how contributors should or should not get in touch with you. And this is an example also of the Turing Way, the contributor MD of the Turing Way. And also very important aspect is to have a code of conduct where you tell participants how you expect them to behave and who these expectations apply to, when they apply, and very importantly, what would you do if a violation occurs? And if you are looking for a code of conduct template, the one in the Turing Way is very thorough, so I really recommend you to read it. You can always reuse it, just the same. And also another part that you should add to your open source code is to add continuous integration techniques. So when you're working collaboratively, continuous integration techniques make sure that every time someone tries to add something to the code does not fail in multiple manners. And continuous integration techniques should be carried out frequently. And the usual way that they are carried out, of course, is by running, but every time, sorry, that somebody tries or opens a pull request, or somebody tries to merge something in the main branch of a repository, CI integration, continuous integration techniques get triggered in the way that you can see here. And there are many continuous integration tools. You have the now infamous, I think, Travis, Circle CI, GitHub Actions, and Azure. The Turing Way has a chapter now on Travis, but during the book dash, we are working on changing it to show how you can actually use GitHub Actions. But the important part is that for carrying out continuous integration, what you need is a YAML file. Depending on the tool, it's going to depend on how you call this YAML file, of course. But in there, you specify the language and the versions of the language that you want to test your coding, and the operating system, and what to do before running those tests and after running those tests. But yes, as I said before, check out the Turing Way guide for more in-depth information. And there are a lot of other things that you should add, or maybe that are nice to add to your open source code. For example, documentation, hosting your documentation online, for example, using Read the Docs. The Turing Way currently doesn't have a guide on how to achieve that, but we are writing one during the book dash as well. How to package also your open source code, and how to maybe add some interactivity to it by adding tutorials in Jupyter notebooks or stuff like that. But maybe these three things are things that you can think of in more depth if what you're trying to do is a toolbox, not a code that accompanies a paper. So I'm not going to explain them further. But yeah, if you want to read more about the Turing Way, here are all the links you can use to do so. I want to really thank Kirsty and Malvika, who always provide feedback on these presentations, and to the whole Turing Way community. And of course, you for listening, and I'm happy to take any questions.